Dear students, welcome you all for this massive open online course on operating systems, and today we are going to discuss about the real-time scheduling in the operating systems course. The topics which we are going to cover today is about the introduction to real-time systems, the classification of real-time systems and priority inversion, real-time scheduling in Windows, RTOS and Linux systems, and various applications of real-time scheduling. So, today the operating systems are purely meant for executing complex tasks, and we have variations of operating systems which are running in constrained devices and embedded systems, where performance of the scheduling algorithms running in the operating systems are very much crucial for its performance. As the name itself says, it is real time. Real time is more focused on how speed we are going to achieve the task. So, the response time should be very low, it should respond very quickly. So, we have mainly there are two latencies that may be there in the computer systems when you execute an operating system. It is about interrupt latency and dispatch latency. So, what is interrupt latency? Interrupt latency is when a process is under execution, if any interrupt arrives to the system, or the operating system handles the interrupt by putting all the previous process in the hold, it continues executing the process which is coming as an interrupt. So, after this it will again go back to the original process and it resumes. So, this process is called interrupt handling, and this interrupt handling process will take a lot of time. So, this is one latency. Second is dispatch latency. So, during this interrupt it has to revoke the process which is running in the CPU, and it has to load the new process. So, this process also will take time. During interrupt it has to execute the interrupt service routine for handling the interrupt, and the dispatch latency is to load the new process into the CPU for its execution. So, these two latencies plays a crucial role, thereby the real time scheduling algorithms which are going to discuss will address these two and how to reduce these latencies. Okay. So, how this interrupt is handled, how dispatch is done faster. So, mainly we use real time scheduling systems like automotive control system, then robotics and embedded devices, medical monitoring and defense applications. All these are mainly focused on functional correctness, as well as it has to meet the deadline which is supposed to achieve. So, catering these two constraints and limitations, we have to proceed with various real time scheduling algorithms. And also in the real time systems, the OS would guarantee the deterministic behavior. So, at this point of time it will complete. So, you cannot have a indefinite time of execution. So, there is a predefined time, as per this time limitation the OS would execute the task. So, basically we classify the real time systems as soft real time, hard real time and firm real time systems. As the name itself says, that soft real time system has, there is no guarantee of scheduling critical real time processes. So, it can schedule at its own time interval, just it will give only one assurance that it give preference over the non critical process. Even if you are not meeting the deadline, still it is okay. In some applications which will accept this. The next one is the hard real time systems. Here there is a guarantee of scheduling critical real time process, there is no deviation, it has a stringent rule. Service after deadline is same as no service. So, if you service a process after its deadline, it is equivalent to not servicing the process at all. So, it is very strict in its requirements. The third one is firm real time systems. It is in between. So, it allows occasional missed deadlines. So, some systems will accept even if you miss some deadline. Missing too many deadlines degrade the system performance. So, it is not like you can miss all the deadlines, but certain days if you miss a particular number of deadlines, it may affect the system performance. We will see with hard real times first. So, here every single deadline must meet without any exception. Even a microsecond delay can lead to dangerous or catastrophic consequences. If you are not meeting the deadline, as I said, it is equivalent to not servicing the service at all. So, if you look at this diagram shows that in this point it shows that if you are not meeting the requirement at the deadline, it is going below. It means that this portion shows that it is as equivalent to not servicing the process. The key features of this hard real time systems are, it ensures absolute deadline enforcement, and there is no toleration of delay or jitter. So, jitter is nothing but variation in delay. So, it has a stringent requirement that it has to complete within before the deadline. The system must be fully deterministic. Yes, we have to be able to say at this point of time this process will get completed and this will initiate the next process, like that. So, worst case execution time must be known precisely. So, everything is well known, and there is no deviation from the benchmarks which already defined. Designed with redundancy, fault tolerance and verification methods, example flight control, pacemaker, these are all systems which requires a stringent rules and deadlines to be followed. Another one is firm real time system, which allows occasional missed deadlines. As I said, we can miss some deadlines occasionally, but any result produced after the deadline becomes useless. So, it allows to miss deadlines, but after deadline the results may not be useful, but overall the system may be useful. That is what about firm real time system. Missing too many deadlines may degrade system performance, but it does not cause catastrophic failure like hard real time systems. So, it is not a life threatening issue. So, deadlines are important, but not as threatening as hard real time. So, late results, as I said, after deadline will be having 0 value. So, there is no point after deadline, requires high predictability, but tolerates rare misses, and it is used in environments where we have stock market order systems, where if you miss some time again you can regain, online transaction handling, network sensor systems. These systems can use firm real time systems. So, if you look at the diagram, so the deadline is here. So, after this deadline whatever you did is not considered, but this will be valid. This will be valid since the firm real time system is not that stringent about its rules. The next is the soft real time. As the name says that it allows frequent deadline misses and late results still provide some value to the system. Even if you execute after the deadline, it may be helpful for certain cases, but if you miss more deadlines, then the performance will degrade gradually. As we already discussed, real time systems need high responsiveness. This is applicable for soft real time systems also. Emphasis on average response time rather than absolute deadlines. So, it is about the average scope, not with respect to specific spots to be responded. Jitter is acceptable within limits. Yes, the variation in delay is acceptable within some limits. No strict guarantee, it is a best effort scheduling. So, many examples we can say in soft real time systems like multimedia players or audio and video streaming. As we all know, audio and video streaming has been accepted by us with a lot of defects because of our eyes property and ears property. For example, in video, even if you miss 1 or 2 frames, still the video can be seen as a real video because of the persistence of vision property of our eye. The previous frame will be retained in the retina for a certain amount of time. So, thereby even if you have missed something, the next frame will come to the retina. So, virtual reality and online gaming, speech recognition systems, all these things will have tolerance about losing some data, still it will be useful. So, the graphs shows that this portion even after the deadline is over, still the usefulness is not to 100%, but still it can be used to some extent. That is what soft real time systems meant. If you look at the parameters we are going to discuss about evaluating this scheduling, we have parameters like capacity, we call it as worst case execution time C, then time period between releases we call it as Ti, and the relative deadline of each process called Di, and this is the diagram. It shows that the task is released at this point, and before the C gets over it has to be completed, and again after the next slot we can restart, we call it as re-release time. So, if the deadline is over, then the task would be completed, else we can go for re-release. So, we will see with some examples of the 3 real time systems. So, the basic requirements of a real time scheduling is predictability is over the throughput. So, we have to predict these are the things we are going to achieve rather than much bothered about the throughput performance. Deterministic interrupt handling. So, we cannot accept indefinite times of interrupt occurring in the system, because the interrupts will suck a lot of time. So, the deterministic approach of real time systems will be broken, and if you allow so many interrupts to occur. So, we have to handle interrupts in such a way that it is not going to affect the time at which we have determined to complete the process. Fixed upper bounds on execution and blocking time. So, we have a static value which says that this is the time at which it has to be completed, it has to execute, this much time it will be blocked because of execution happening by some other process. It supports preemption. So, preemption, as we all know in operating systems, that if some process is holding the CPU, if another process arrives is having higher priority or some other preference, then you have to take this process away from the CPU and the CPU will be assigned to the new process. This is called preemption. So, the real time scheduling should have the support of preemption. So, low scheduling overhead. So, the scheduling itself should not be an overhead for the system. So, the process will be simple, otherwise the overall latency will get increased and the performance will degrade. So, the real time system should handle three types of tasks that can arrive. One is periodic task, which you all know that it comes in regular intervals, and aperiodic task which won't come in regular intervals, we cannot predict when it will occur. The third is sporadic tasks which will come at a periodic way, but the inter arrival time is minimum. We can easily estimate the arrival time, minimum arrival time between the two occurrence. So, these are the three ways the tasks may occur, and all these three tasks can be handled by the scheduling algorithms. So, the types are static scheduling. So, here it is offline, where priorities are assigned before execution and used in safety critical odd real time systems, where we know which has to be done first and which has to be done second. It is a template already fixed, that is called static scheduling. Dynamic scheduling is very difficult, as it is priorities change based on deadlines or laxity. Laxity is the time, remaining time available for completing this execution. So, this has to be dynamically monitored based on the occurrence. The third one is preemptive scheduling, as we discussed just now. The operating system can interrupt a running task and switch to a higher priority task immediately. Non-preemptive scheduling is once the task starts executing, it continues till its completion. No other task can come in between and take this task away from the CPU. These are the various types. And the algorithms which you use basically for implementing this scheduling tasks are rate monotonic, we call it as RM, and earliest deadline first, EDF. So, these are the major two algorithms which we use for handling the real time scheduling. We will discuss each algorithm in detail. We are going to see about the first real time scheduling, that is the rate monotonic scheduling algorithm. So, it is a fixed priority scheduling algorithm. So, the priority is always static and it is preemptive. So, as we already discussed, preemptive is we have to take the process which is running in the CPU and we have to assign the CPU for the new process which is coming in. And we know that the priority is based on period. Period here refers to the process which is having the shorter period will be given the higher priority. So, that is the main theme of rate monotonic scheduling. And other assumptions like independent periodic tasks, each task is independent and deadline is equal to period, and the preemptive kernel, as we all say that it will take the process assigned before in the CPU and it assign new process, and the process duration of the CPU bus is same, that is for each period the amount of time it is assigned the CPU is same, there is no change in that, and it is proven optimal for fixed priority scheduling. So, this priority scheduling is always suitable for fixed priority. If you look at this diagram, it shows that there are three processes. So, each is T1, T2 and T3, which says that it needs the values 4, 1, 5, 2, 7, 2 says that the period. So, out of these three, the first one is having period value 4, the second is having period value 5 and third is having period value 7. So, out of this, the lower period will have the higher priority. So, this will have priority 1 and this will have priority 2 and this will be having priority 3. So, the 4 represents the period. So, if you look at the first higher priority process P1, it has value 4. So, from this is 0 and this is 4, 1, 2, 3, 4, and here it is 0, 1, 2, 3, 4, this is 5, 0, 1, 2, 3, 4, 5, 6 and 7. Since this is higher priority, it says 1. So, for each period it will execute once. So, 0 to 1 is 1 and the second priority process has 5, 2. So, its deadline is 5. So, it executes 2 slots. So, first slot is occupied by process P1 priority process. So, the second and the third, because it is 2, P2 will occupy this 2, and the third one is the third process. So, it occupies this is by P1, this 2 by P2 and this is by P3, lower priority process. So, after this deadline for T1 occurs here. So, this is the deadline for T1. So, since deadline for T1 occurs, the next period starts. So, during this next period, the higher priority process P1 will occupy this slot. So, P1 will occupy this because P1 deadline is over here. So, the next period is starting for P1. So, in that period, the first slot will be assigned to P1. So, now what is happening? P3 is already assigned. Still it has to complete another one before its deadline 7, but it is taken back. This is called preemption. It is taken back and given to P1. So, now P1 will execute here. So, this is P1. After P1, the next priority process is P2, which has to be executed for 2 slots. So, here P5. So, from here to here P2 will occupy. It is shown here. So, after this it reaches 7. Actually, the deadline for process P3 is 7. So, deadline is expired, or deadline is reached, but still one more slot of P3 is pending. Only one is done, another one has to be done before this deadline, but it is not done. So, this is called deadline miss. That is the problem with rate monotonic scheduling. So, it gives equal burst for all periods. So, it is most suitable for fixed priority scheduling. So, this problem can be overcome in another scheduling algorithm. That is how the scheduling algorithms are designed. So, we will go to the next one. Before that, we will discuss about how the scheduling test is done. For n period tasks, CPU utilization U is given as the capacity divided by the time period. So, the process can be scheduled, task can be scheduled if the upper bound, that is the bound value U, it is utilization U is less than or equal to n and 2 power 1 by n minus 1. So, this is the condition to check whether it can be scheduled or it cannot be scheduled in rate monotonic scheduling algorithm. For example, if n is equal to 1, the full system is going to be assigned, so it will be 100%. If you have n is equal to 2, then it will give value of about 0.83, and if it is n is equal to 3, the task, it will give about 0.77. If you go like that, if n is equal to infinity number of tasks, then the performance will be 0.693, that is approximately equal to 69% of utilization. This is what is given here. If for larger value of n, the bound is 16%. So, it is the fixed. So, CPU utilization is less than or equal to bound, all deadlines are guaranteed, otherwise the deadlines may not be guaranteed, there will be miss meeting out the deadline. So, practical performance is often higher if fixed values are given for priority and it is maintained throughout. That is the beauty of this algorithm. So, you will see the advantages. The algorithm is very simple and predictable. We can easily predict, because based on the number of tasks available and the period for each task, we can easily predict when this task will be completed, and low overhead, strong theoretical basis. Yes, it has rules is set clearly that it is a preemption algorithm which is having fixed priority throughout, and the limitations is works only when deadlines is equal to periods. So, otherwise the deadlines miss will happen, it will not work. So, if it is all coming within the deadline, then this algorithm will work smoothly. It cannot handle overload smoothly, because if there is too much of overload, then many tasks may miss the deadline. It is not appropriate for that, and it is suboptimal for sporadic and aperiodic tasks, because these are all tasks which will occur in indefinite times. We cannot have a constant period of occurrence of these tasks, we cannot predict. So, this is not that appropriate for this type of tasks. The second algorithm is earliest deadline first scheduling algorithm. So, it is a dynamic priority algorithm, whereas that one is static. So, this dynamic priority is assigned based on the remaining deadline time available. So, the priority keeps changing based on the deadline for any process. The task with the earliest deadline gets higher priority, that is what is optimal among uniprocess scheduling algorithms, highly flexible for varying workloads. The earliest deadline first schedulability is feasible if this equation satisfies, that is the capacity bar time is less than or equal to 1 for all process I to n. So, it can achieve 100% CPU utilization, because if a particular process is done, if the second process is yet to be finished, if the deadline, it will check the deadline. If the deadline is coming earlier to any process, that process will be given higher priority, thereby always it will be utilizing the CPU. It offers higher schedulability than rate monotonic, because rate monotonic will keep the slots idle if it is not meeting out the requirement. So, it is highly sensitive to overload conditions, that is the one drawback of this algorithm. We will see with this example. So, we have first scenario is given as A1 and B1 both are arriving at the same time. So, A1 is arriving at the same instant, for example, 0 la both are arriving at the same time. As we say that earliest deadline first is, since A1 deadline is 20, this is the deadline for A1 and this is the deadline for A2, for A3, A4, A5. Similarly, this is the deadline for B1 and this is the deadline for B2. So, A5 and B2 are having the same deadlines. If you look at this diagram, you can see A1 and B1 are arriving at the same time. Since A1 deadline is low, for example, deadline for A1 is in this example is 20 and the deadline for B1 is 50. Now, A1 is having higher priority than B1. So, it is giving A1 as the first priority A1. So, A1 is given the first priority, then B1. So, since B1 is having 1, 2, it is giving the B1 for the next priority. So, here you have B1. So, A1 is done and B1 is done. Now A1's deadline is 20. So, after this 20 we have the remaining deadline we have to compute. So, what is the remaining deadline which is left out? Here we have A2 deadline is 40. So, if you look at this example, since A1 deadline is 20 and B1 deadline is 50, A1 is having higher priority. So, you are giving A1 the first slot and B1 the second slot. After this A1 deadline is met and we have the second one, whereas second period we have A1 deadline is 20, but after that A2 is arriving. So, when A2 arrives, what is the deadline of A2? A2 is 40. So, when you compare A2 and B1, A2 deadline is coming earlier than B1 because B1 deadline is 50, whereas A2 deadline is 40. So, A2 is getting higher priority than B1. So, we are giving for A2. Next only we are giving for B1. So, after B1, the B1 deadline is 50, whereas A3 arrives after this B1. So, A3 deadline is 60. So, since A3 deadline is 60, when compared to A3 and B1, B1 priority is higher. So, B1 is continuing after this slot. So, it is executing for 2 slots because the deadline for B1 is smaller than the deadline for A3 because it is 60, whereas for B1 it is 50. So, after this A3 is executed. So, after A3 executes, then B2 is occurring. So, B2 occurs here, but the deadline for B2 is 100. So, B2 is having the least priority now. After A3, then you give B2. After this A4 arrives, so we have to preempt. So, here we are doing preemption because the deadline for B2 is 100, whereas deadline for A4 is 80. So, we are giving priority for A4. After A4 completes, then we have the slot, then we can assign for B2, then B2 executes up to 90. After this, we have A5. So, A5 at this point A5 arrives, A5's deadline is 100 and B2's deadline is 100. So, B2 is getting completed, then you are assigning A5. So, this is how the priority keeps changing and all the subsequent tasks will be executed. We have made so many context switches here, context 1, then 2, then 3, 4, 5, 6, 7, 8. So, 8 context switches has occurred throughout this execution, but the entire thing slot is the CPU is kept fully occupied. So, A1, B1, A2, B1, A3, B2, A4, B2, A5, all these processes are occupied the CPU. That is why it is we can say it is 100% utilizing the CPU. Only thing is many context switches will happen, and if the load is heavy, it is highly sensitive, that is the problem. So, it always switches by assigning dynamic priority to the process which is having the earlier deadline. So, if you look at the advantage, it utilizes the full processor capacity, simple mathematical schedulability, it just calculates the earlier deadline and it schedules. It is ideal for soft and firm real time systems where it is utilize the slots effectively. Drawbacks is priority changes frequently, it changes the frequent priority of the process frequently and highly complex in implementing OS kernels because of this issue. So, missing deadlines under overload leads to cascading failures. So, if it misses the deadline for a particular process, then it will affect the forthcoming assignments also. That is the drawback of this EDF. How to handle the tasks which are occurring in different ways, for example, periodic, aperiodic, sporadic. Periodic is the tasks which are occurring at regular intervals. Aperiodic we cannot assume, we cannot predict when it will occur, and periodic is, it is also aperiodic, but the minimum interval time is constant. We can predict, it cannot happen immediately, it will happen after a regular intervals of time. So, this is 3 types of tasks that can occur. We have dedicated servers for handling all this. We call it as polling server, deferrable server and sporadic server. All this will handle tasks which are occurring at periodic, aperiodic and sporadic way. The next is the priority inversion. For example, there is a problem with the Mars Pathfinder spacecraft failure caused by unbounded priority inversion. So, it is about the how a lower priority process holding a resource and it is locked by a medium priority process, whereas the resource is expected by higher priority. So, we have to change the priority, thereby we can assign the appropriate task to be done at the respective time. So, for that we have to change the priority of the process based on the situation. We call it as priority inversion. If you look at the Mars Pathfinder spacecraft failure article, you can understand that how changing the priority helps in recovering this problem. So, the solution for this priority inversion is we can implement using various protocols called priority inheritance protocol. We call it as PIP, and it is a low priority task protocol which temporarily inherits the priority. for the certain period of time it changes the priority of the particular process and again it will come back. The second is priority ceiling protocol. So, it will say that this resource should have the maximum of this priority, it should not cross beyond this priority level. This is called ceiling protocol, and ICPP is the immediate priority ceiling protocol, which is very stringent protocol, which says that prevent deadlock and limits blocking time. It is used in all the operating systems which has real time constraints. So, how this scheduling is implemented in various operating systems in Linux? We have these routines for implementing this real time scheduling by using the appropriate calls like schedule FIFO for first in first out, and it is for round robin, and schedule deadline that implements the EDF algorithm which we discussed. So, by using the respective calls mentioned here. So, the Linux real time features offers high resolution timers, then preempt real time patch, bounded interrupt latency. All these are all features of real time Linux operating system. Similarly, we have things for Windows where Windows preempts lower priority threads when a higher priority thread becomes ready. So, we call that as in three ways: normal, high and real time. So, based on this we can assign the priority for the thread. A relative thread priority determine which ready thread runs to be next. Then real time class can stop system task if used carelessly. So, if you look at this code, we can see that can assign priority using the functions called set priority class and set thread priority. So, here we have a group of classes. For the current process we can assign this priority class, real time priority class. Out of many number of classes, this real time priority class is one class that we can assign to this process. Second, if you use for thread also we can use. So, get the current thread which is under execution and you can assign this specific thread priority. We call thread priority time critical, which is very stringent rule that can be assigned to the threads. So, this is how real time scheduling can be done in Windows. If you look at the main real time scheduling in real time operating systems which we run mainly in embedded systems, it has to ensure faster context switching and predictable real time behavior. There are various examples of the real time RTOS. We have VxWorks. The example which we discussed is that Pathfinder which uses VxWorks, and we have QNX, Free RTOS, RTMS. These are all various examples of real time operating systems that is running in embedded systems. If you look at this code, we can see we can have we can create a task of, let us take task A and task B. You can assign name for the task for our understanding, which is not involving any scheduling process, A and B. And if you look at this, this is the stack size which you can assign for the task. And the number, the null is normally we assign null as a fourth argument, and 1 and 2 represents the priority. So, the lower the value will be having the lower priority, higher value will be having the higher priority. That is the interpretation which is embedded in the RTOS system. So, we have these values represent the priority level for the tasks. So, if you execute this, if you call the scheduler will schedule this one first and this one second. This is first and this is second. This is how scheduling will be done. So, it is example for real time operating systems. So, the applications of real time scheduling is implemented in various real time applications like autonomous vehicle, medicines, industrial robots, where the reactions will be very faster, and telecom based stations, multimedia streaming systems, and defense aerospace control systems. So, we have discussed about the various real time scheduling, importance of reducing time in scheduling and assigning the tasks. So, how rate monotonic is assigning the task with the fixed priority algorithm. Then we have the EDF, which is a dynamic priority algorithm, and how we are handling the sporadic task. Avoiding priority inversion is essential. Methods which can handle the sporadic tasks which is occurring aperiodically, and overall we can say that real time scheduling is the foundation for modern embedded and mission critical systems, which is quietly familiar these days. So, with this I conclude this presentation. Thank you.